Hello, everyone. In this video, we're going to look at example 3 in section 8.5 on Taylor series and Taylor polynomials. So in this example, we use some of our results from exercise 3 in the examples and exercises in this workbook. So what I'd like you to do is pause the video and work through exercise 2 on page 120 before continuing. It's really important that you go through that exercise on your own or with others in this class, but without just watching the video so that you can really confront some of the topics and how-tos for computing Taylor series and Taylor polynomials. All right, so in a little bit, I'm just going to share with you the solutions to exercise 2. So this is your last chance to pause the video. All right, so I've just scrolled down here to exercise 2 in our section 8.5. So I'll go ahead and share with you the solutions for exercise 2. So here we're asked to find the Maclaurin series, so the Taylor series centered at 0, for the function f of x equals sine of x. So in the end, we should be getting the Taylor series that looks like x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th, etc. So a couple cool things, we can recognize this as an alternating series. N equals 0 to infinity of negative 1 to the n, x to the 2n plus 1, all over 2n plus 1 factorial. So then in part B, what you were asked to do was to use some of these Taylor polynomials of degree 3, 5, and 7 to approximate the value of sine at 2. And then to compare your calculations with the value of the function sine of 2. So I'm going to go ahead and share those solutions because we're going to use them in the example 3. So the third degree polynomial evaluated at 2 is going to become 0.666 repeated, or 2/3. P sub 5 of 2 is equal to 0.9333 repeated. And then P sub 7 of 2, or the 7th degree polynomial, is 0.907937. All right, so now let's go ahead and scroll up to example 3 and get started there. All right, so example 3 says, in exercise 2 on page 120, you used P3, P5, and P7 for the function f of x equals sine of x to estimate the value of sine of 2. Find the maximum error in each of your estimates and complete the table shown. So in this example, we're going to be able to use that error approximation to determine the error for each of our Taylor polynomials. All right, so let's just write down some reminders about that exercise. And this will be useful in helping us write out that error formula. So notice this error formula includes A, which is what our Taylor polynomial is centered at. And it also includes C, which is the value that we are the value that we are using to evaluate our function on. So what is R, A, and C in this example? Well, A, our Taylor polynomial was centered at 0. So A is 0. C, we are evaluating our function at 2. So C will be 2. And then recall our P of x looked like x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. We alternated and we had just odd exponents and odd factorials in the denominator. Okay, so that's just kind of our setup. So now let's continue. So we're going to find the maximum error of each of these estimates and complete the table. So let's go ahead and work in this table. So we want to compute in this first cell, P sub 3 of 2. So we already computed that in exercise 2. So I'll just repeat those values here. So feel free to pause the video and then skip ahead and repeat them on your own or rewrite them here on your own. All right. So for each of our Taylor polynomials, 3, 5, and 7, we're going to use this error approximation to determine the error or a maximum for the error of each of them. All right, so let's go ahead and write out some things. So we're going to do our error approximations here. Okay, so let's start with when n equals 3. So when we're looking at n equals 3, we want to find e sub 3 of 2. So to do that, we need c, a, n, and m. So most of these things we know, c, a, n. We need to determine m. So to do that, we need to look at the nth plus 1 derivative of our function. So we'll just make some notes here on the side. This is kind of some scratch work. So for when n equals 3, we need to find the m associated to n equals 3. So we need to consider the 3 plus 1 derivative of f on the interval from 1 to 2. And so just a note, x is on the interval from, and not 1, rather 0, that's our a, to 2. Recall that's a to c. So to do this, we need to compute that fourth derivative of x. So let's go ahead and write those out. So the first derivative of x, well, it's f of x. Let's just write that instead. Let's start with f of x is equal to sine of x. So then the first derivative is just cosine x. The second derivative is going to be negative sine x. The third derivative is equal to negative cosine of x. And the fourth derivative is equal to sine of x again. So then we see that if we look at the absolute value of the fourth derivative of x, that's equal to the absolute value of sine of x. And we need to determine a number, m, that is a maximum for sine of x on the interval from 0 to 2. So this is how we are finding our m. So now what I'm going to do is pause, clean this up a little bit, and just write out again what m is so we can see it in writing. So this m is the max value of f of 4 of x, which is the absolute value of sine of x, on the interval from 0 to 2. So let's just recall sine of x. It's a nice function that bounces between -1 and 1. So then the absolute value here would just look like lumps like this. So then we see that the maximum that sine of x absolute value can be is 1. So for us, this m is 1. Cool. So we found every component that we need to write the error approximation. So let's go ahead and write that out. So we see here that the error of the third degree polynomial is going to be less than or equal to m times c minus a to the power of n plus 1 over n plus 1 factorial. All right, so let's fill this in for us. So we saw that m was 1. We have that c is 2, a is 0, n here is 3, so we raise to a power of 4, and then we divide by 4 factorial. Okay, so let's go ahead and compute that out. So we get 1 times 2 to the 4th over 4 factorial. And we compute that out, we get 16 over 24. And you can check me, which is going to be, if we simplify it, it's 2/3. or 0.666 repeated. So what we just found is that the maximum error of our third degree polynomial at 2 is 0.66 repeated. Meaning the difference between, we know we are for sure that the difference between our polynomials value at 2 and our sign or our function value at 2 is 2/3. So you might be thinking to yourself, well, that's not a super great approximation. Well, let's look at what happens as n gets larger. So now let's do the same practice, the same routine for when n equals 5. So we're going to go a bit faster here since you've already seen the steps for how to do this in n equals 3. So we can speed up a little bit for n equals 5. So we need to compute the m. So in our case, that is, we need to look at then the 6th derivative of x, of f of x rather. And so if we continue that work, we saw the 4th derivative was sine. So the 5th derivative would be cosine. So that 6th derivative is going to be negative sine. So this is equal to the absolute value of negative sine of x. So we need to determine an m that's a maximum for this function on the interval from 0 to 2. We see that again is going to be 1. So this is the max value of sine of x, negative sine of x, on the interval from 0 to 2. So let's go ahead and write out that error or compute that error estimate or maximum error. So the maximum value of the error is going to be less than or equal to 1, which is our m, times c minus a to the 6th over 6 factorial. So again, that looks like 1 times, so 2 minus 0 is just 2 to the 6th over 6 factorial. So you can go ahead and compute that in your calculator. You should be getting something around 0.0889. So this is the max error of not e, but of our 5th degree polynomial at 2. And so let's go ahead and make sure we're filling in this table as we go. So recall the error for e, for the error for the 3rd degree polynomial, i.e. E3, was 0.666. And then for P5 was 0.0889. So we'll fill that in up here just so that we're keeping track of our work. So we have 0.666 repeated. Then we get 0.0889. And what do we notice as the n increases? What do we notice between the error for P sub 3 and P sub 5? The error is getting smaller, which is what we should expect. As we use larger values of n, so Taylor polynomials with more terms, our error should get smaller because our outputs get more close to the function value. All right, so let's go ahead and finish this example off by looking at when n equals 7. So again, we're going to go through this kind of quickly because now we know we're getting familiar with the steps. So when n equals 7, we need to look at the 8th derivative of x. So you can check my work, but when we continue taking the derivative of our function, we're going to get sine of x again. So here, conveniently, we're going to get the same m. So then the maximum error of our 7th degree polynomial will be less than or equal to 1 times, we're still going to get that absolute value of 2, but now raised to the 8th divided by 8 factorial. So when we compute that out, you should be getting something around 0.00635. So filling that into our table. All right, so we're going to fill in here 0.00635. And notice what is happening with these numbers? Well, that error is getting even smaller. So telling us that as we increase n, the value of our nth degree polynomial at 2 is getting closer and closer to the function value at 2. Awesome, great work.